actually we focused on two variables, functions of two variables. So we'll continue to talk a little bit more about that, and then we'll extend it to even more variables as needed. And so we talked about the numeric point of view of these things by looking at some tables. We talked about some formulas, and then we got into a little bit of the graphing, and we were able to view some simple graphs by looking at level curves. So I don't know if you guys are familiar with topographical maps, but those also are forms of visualizing a three-dimensional thing and viewing it on a two-dimensional picture. So the idea is to reduce your three-dimensional graphical picture to a two-dimensional graphical picture and still be able to get an idea of what's happening in 3 dimensions. So I don't have any ready pictures, so let me look in the internet real quick for some topographical maps and talk about them. So, do you guys know what a topographical map is? Yeah?
It's like a normal map that shows when there's a change in elevation.
Shows changes in elevation. So, these are complicated. There are some simple ones. What if we just put topo? Now, let's take a look at a map that looks like this. And what you have here generally for topographical maps, what you have is a bunch of curves, and if we're talking like a mountainous type of terrain, they would generally be closed curves, so curves that end up closing itself, that has a given height of something, and what that does is it tells you at height of 900 feet, let's say this is in feet, in the height of 900 feet, you can walk around this mountain on this path and your elevation won't change. Okay, so let's say in 3 dimensions you have some mountain ranges, and then you fix a particular height, and what you get out of that are these levels of the same height. And so what we're interested in is kind of viewing this on a map. To say at some certain height, this is what we're getting And then if we cut this at a different height, maybe slightly higher, this is maybe what we'll see. And then slightly lower, we'll see something else. But whenever you get these closed curves, then we know that there's going to be a peak or a valley somewhere. It's going to be a high point and a low point. Okay? Now, topographical maps give you the height for every x and y point that you have. So if you're given an x, if you find yourself in an xy point, this is a point in some xy coordinate. You can think about it as longitude and latitude. Then at that point, your output value of your function will be your height, and then that tells you how high you are above ground. So in this case, this would be a function of height. Okay? But it turns out height isn't the only two variables to one variable mapping that we can come up with. There's also, I don't know if you guys have seen temperature maps. You guys familiar with temperature maps? So an example of a temperature map could be something like you have a map of a state or a whole country or a city or whatever, and then you have different shades for different temperatures. So a temperature map takes in an XY coordinate, longitude, latitude, if you want to think about it that way. It takes in an XY coordinate, and then it gives you the temperature at that XY coordinate spot. And here now, the temperature is described by the shading. So this could be my function t, capital T, that takes in a couple of values, a couple of real numbers, and then outputs a real number for the temperature. And here you have a range of values, so let's randomly pick, let's say in California here, in Redwood City, we're in the yellow, so we're looking at our output to be somewhere between 65.1. Did I go up? Oh, 55. 55 to 60-ish. So we're looking at the temperature at this point to be somewhere between 55 to 60. Okay? So the shading on the map also is important if you see the shades. And in fact, that's a special kind of graph. You remember what this graph was? You remember? Come on, guys. It's a what? Parabolic hyperboloid. No. Switch it around. Switch the adjective and the noun. Hyperbolic paraboloid. Okay, it's a paraboloid because it has x squareds and y squareds, but there's a minus in between, so the cross sections are hyperbolas. So hyperbolic, the noun itself is paraboloid. So anyways, if I graph this, we get the saddle shape, but let's look at the graph a little bit differently. And it says here I can draw a density plot. That's not a very nice looking density plot. Let's see if we can. So a density plot gives you a shading, a color shading, and usually at the higher points, my shading is lighter. It depends on how the algorithm is used, what kind of algorithm they use to differentiate the shading. But looks like if I'm over here in the lighter shading, I'm going to get values that are, it says 161, so that's up high. And then if I move my cursor over here where I have a darker shading, I have a negative 56, so it goes down low. So it goes dark, low, dark, and then it goes higher and higher, and then the color gets lighter and lighter. So the contour shading gives you different shades of color as you get as you change in your output. So if your output is let's say this is a mountain. If you take a look at that graph again, how can I take a look at the graph? Oh, surface plot. So if we take a look at that, imagine this is like a valley that goes down. Let's say this is in the middle of a mountain, and then you have a mountain going up, and then if you go down this way, you go down the mountain. Then if we take a look at this as height, then the different changes in height will change by color. Or you can also take a look at this as a temperature, where the higher you go, the colder it gets, kind of thing. So you can take a look at that from that point of view. By the way, have you guys ever seen a mountain like this?
The valley would be closed in also.
Yeah, a valley would just be a dip in the thing, right?
That's just what happens when there's two peaks right next to each other.
Kind of, but then it has to go down on the sides also.
Right, but no, if you have like
Yeah.
approximation of two cones next to each other in the middle of the lake.
Should I do this? Actually, yeah, move it. It's in your book. This is a perfect example of a saddle. You can almost see the contours. Actually, let's take a look at the contours as contours. So hyperbolic paraboloid, remember it's x squared plus y squared gives you the paraboloid part. And the cross sections, if you take the level curves, they're hyperbolas. And so if you take a look at this, even that x over here, you can actually see it on this graph. Kind of cool, huh? And all that different layers of sediment, you can actually see the levels. All right. So that's topographical maps. Should we take pictures of this? I think this is cool. Put it in our notes. If we compare that with the graph, first the saddle. and then the contour plots themselves and then the density plot that gives you the different levels of the contour by color. Then you can see the three sort of graphical representations, a visualization of the same shape. Okay, these are all describing your saddle. And we can do this for any sort of shape or any sort of function that we have. All right. So here's another interesting application to this, I guess, before we move on to even more variables. See, I'll just write it. So T of xy is equal to 78 minus 1/10 x squared plus y minus 5 squared. So as a temperature is a temperature function in a 10 by 10 room. So one corner is going to be the 0, 0 corner, and then the other corner would be the 10, 10 corner. So what we could do is we could try to draw the function, draw the temperature function. I don't know how easy it's going to be, but let's see if we can draw the temperature function here. Instead of drawing it in 3 dimensions, which I guess somebody can possibly do, maybe we can try to draw this using some sort of level curves. And draw the graph of temperature function, describe likely the floor location where the heat vents are, and if you like sleeping at a 70-degree temperature, where would you sleep? So let's answer that question first. Where would you want to sleep at 70? Where is this going to be 70 degrees? How would you find that? What would you do to find that? Where what? Where would you sleep if you want the temperature to be equal to 70 degrees? It says 70 degrees or less. What? Yeah, if we make the whole thing equal to 70, that's your temperature, right? And this is your temperature equation, so let's let the temperature, the T itself, equal to 70. So 70 is equal to this thing, 78 minus 1/10 and all this stuff. So it doesn't look like I'm going to be easily able to solve for x or y by itself, but if I can just keep the x's and y's together in one side, maybe I could still deal with this. So this would be a -8, divide by or multiply by 10. Make that into a positive. I think this is going to be 80 on one side. Is that correct? Is equal to x squared plus y minus 5 squared. So now it looks like an equation of a circle. Radius square root of 80. What's the square root of 80 about? Can you, somebody punch it? 9-ish? 8.9? Let's go 8.9. What? Yeah, well, what does the 5 over here do? Shifts it, right? So now our center is not at 0, 0, but where's our center? 0, 5. So at 0, 5 with a radius of about 9. So this is 10, so a little bit less than that. This is your circle at 70 degrees. So if you like sleeping at 70 degrees, you would be somewhere along this. Of course, outside, you're not in the room anymore. So we kind of want to ignore that, and we just want to focus on these values. Okay? So what's the temperature exactly here, you think? What's the temperature at this point, 0, 5? It would be 78. So at 0, 5, this whole thing would be 0. So let me write that down a little bit more formally. T of 0, x is equal to 0, y is equal to 5, is equal to 78 plus all that stuff kind of disappears. So you're 78 degrees at this point. Does that make sense? And then so it looks like as you go further and further out, you're going to get colder and colder. Right? So over here, your temperature is going to be less than 70 degrees. So where do you think the heat source is? At the center over here, that's where it's warmest, right? So people tend to think that when you have functions of two variables and you get to view this graph, then the graph automatically refers to a mountain or some physical range where we talk about the height as your output. But it's not always like that. So like in this case, the output is the temperature, is not necessarily the height. And by the way, you can graph this. If you were to graph this, what would this look like? So let me see if I can simplify this idea of graphing it by just looking at z. Can or can't what?
Graph it.
Oh, yeah, we can. We can graph it in 3 dimensions. So instead of a t, this is your third variable. You have an input variable of x and y, variables of x and y, and then your output variable would be your third variable. So if we call that z, then you have something like this, which you can manipulate around to make it look something more describable based on stuff that we've studied already. This is a quartic section. Quadric. And so if you move things around, then you might see what this is equal to, or what this might look like. It's a what? What? Paraboloid, yeah. So this is a paraboloid. It has an x and a y, and they are both positive. Well, they both have the same sign. They'll end up being negative. So this would be a paraboloid with a negative outside, making it upside down. And then there's a shift in the z. So at that center, this is equal to, what did we say it was equal to? 78. So let's see if we can draw this in 3 dimensions. I'll draw the axis in black. And our special point on the xy plane is 0, 5. So 0, 5 would be along the y-axis. And at 0, 5, we have a height of 78. So let me put that in 3 dimensions. 0, 5, 78 is your height directly above this point, 0, 5, 0. I didn't put the comma 0 there, but and then you have a paraboloid turned upside down like this, maybe a little wider. I don't know exactly. And then that's your. It's probably a lot wider than that because in a 10 by 10, the temperature just moves from 78 to 70, probably not even past 60. So. Yeah, it's not a very wide range. So, so the step to go from one level to another is a small step. And so, actually, let me see if I can draw this a little bit more accurately. I think it'll be. I need to be able to go in a 10 by 10 room, and this thing only goes past 78 or 70, maybe 65. Okay. All right. So that's kind of a neat non-height example of functions of 2 variables. All right, now let's go into more variables. And one of my favorite examples that talks about functions of more than one variables would be your grades. Your grade is a function of 5 things. And it's a simple function. If you take a look at your I was going to be able to pull a syllabus up real quick, and now my computer's frozen. Anyways, let me just make it up. So your grade, let's call it G then for grade, is a function of your homework, the labs, quizzes, the exam, the final. Is that it? I think that's it. So this is a simple function. It's just a linear function, and each of these have their weights. So we can think about this as what's your homework? 10% of your grade? And then your lab's like 5%. And then your quizzes are 10%. Your exams are like 20, 25. And then your finals, whatever's left to make 100%. This isn't right. 35, 65. I don't think that's right. I hope it's not right. Man. So this is a function. It takes in 1, 2, 3, 4, 5 inputs, and then gives you a number for your output. And whatever this number is will be your score, your overall grade for the class. Right? So more reasonable example. Well, not more reasonable. Oh, by the way, I also think about this as to compute your grades, I think of a dot product. I would dot your grade vector with the weight vector. So I would make a vector out of this, the weights of your grades, the categories, and I would just dot it with your list of your grades. So you can also think of this as a vector dot product. Anyways. 55. It's 110. If I take away 5, it becomes 100. No. Yeah, whatever the grade book says. Your syllabus, whatever your syllabus says. Anyways, let's go down to something that's a little bit more interesting in terms of from a graphical perspective. Because right now, with 1, 2, 3, 4, 5 variables, by the way, this is a Q or G. That's your grade. Takes a vector of 5 numbers and gives you a scalar, a real number, for your output. All right, let's do a different one. Let's take a generic f function that goes from R3 to R. Because we're going to be studying R2 to R a lot, but then we're also going to be looking at R3 to R in some detail. And an example of this would be something like f of x, y, z. This time I have x, y, and z because I need 3 variables to put in. And then my output would just be regular variables. So if I just say x squared plus y squared plus z squared or something like that, then this would be a function of 3 variables. So in terms of this being a function, we could put in values for x, y, and z and get things numerically, and we can set up a table. Actually, the table will have to be a 3-dimensional table because I need x values, y values, and z values. So that'll be hard to picture. You could have a couple of pages of this table as like the 3rd dimension, but you know, a table within a table. Anyways. But the interesting thing is that we can still try to get a glimpse of this graph. The graph of this is kind of weird, but we can still get a glimpse of this graph. How? We can't visualize something in 4 dimensions, and this has an x, a y, and a z, and then a 4th output variable, so we can't visualize this in 4 dimensions. We can only visualize things in 3 dimensions. So how can we use a graph to represent this function? Yeah?
Maybe something along the lines of if we take like what we know that x squared plus y squared is a circle, right?
Mm-hmm.
So we could take that, imagine that's just the circle, and then we just have a z dimension, which is just, I guess this might be some sort of cylinder or.
No, I thought you were going in the right direction, but then you took that cylinder turn, so no. But that's good. That's a good idea, right?
Wouldn't that be kind of something sort of like an electron cloud, where it's like a sphere, but it's like darker in the center?
Ah, yeah. So that's getting a little warmer. Yeah, or maybe that did hit the spot. Do you guys know what she's talking about? How would you do that? Yeah, like not just coloring it in, but how would you express that symbolically? With this equation that we have, what would you do? Anybody? She's got the idea, yeah? Yeah, but how do we create the different layers? That's the question. You guys are on the right track, or at least these two are. I don't know if you guys are. But they're on the right track. Layers. Yeah. You set the output equal to what? Different numbers. We did that. What did we call that when we set the output equal to different numbers? Good job. What? Traces. A trace or a level curve. So a level curve is setting the output equal to a bunch of different numbers. So let's just call this, since this is not going to be a curve anymore, let's call it a level set. And level set would be a more generic name for a level curve or anything else higher. So our level set is by letting the output equal to some constants. And what do we get if we do that? We get, for this particular function, if we let 0 equal x squared plus y squared plus z squared, if we let 1 equal to x squared plus y squared plus z squared, and concentric, not only shell, what kind of shells are we looking at here? These are spheres. I think we had the same setup last time, except I didn't have a z squared, just x squared plus y squared. And so here we have concentric spheres, spheres within spheres, that would hope to describe this four-dimensional object from a three-dimensional point of view. So the level sets would be concentric spheres. And you can attempt to draw this. Page what? Oh, did I use the same example? I didn't want to use the same example. Yeah, maybe I should have done something with a cone, where outputs are cones instead. Anyways. So here's a view of this concentric circles, and they are surfaces in this case. So for this special case, they happen to be surfaces. So we can take a look at level surface as a surface that came from a function of three variables. No, there's still surfaces. Like Mariah was talking about, like different shading. You can think about solid balls with different shading going out, but technically you're still peeling them as spheres. Level sets for functions that go from R3 to R give surfaces. So we tend to call them level surfaces. And your task is to be able to look at an equation with 3 variables and be able to tell what kind of surface that is, which is why those quadric sections or quadric surfaces are kind of important, because you might be asked to describe this surface. In this case, it's a sphere, but you want to be able to describe cones and paraboloids and hyperboloids of 1 and 2 sheets and stuff like that, if you need to. All right. I think we need to move on. So I think that gives you enough ammunition and information to tackle the homework. Let's go on to the next section. I have notes for the next section. So the next section talks about limits and continuity. I don't really want to talk too much about this. But in general, most functions that we deal with are continuous, right? Nice polynomials. So most functions and I hope you're comfortable with this notation now. A function going from R to R is just a regular real number functions. 1 in and 1 out. So your 1 in is X, your 1 out is Y. So that's something that you guys have studied all throughout your pre-calc careers. And most functions that you guys have looked at are continuous. And you really only looked at functions, we really studied limits when we're taking a look at weird functions and piecewise functions and things like that. And so examples of continuous functions that you guys have dealt with are polynomials. Polynomials are continuous everywhere. Your exponential functions are continuous everywhere. Your log functions are continuous except for the places where they're not defined. So as long as you're within the domain of your log function, you're continuous. Your trig functions are continuous except for some of those, the tangent, the cotangents, and the cosines and cosecant. No, not the cosine. Well, whatever. As long as we specify that, as long as we're in the domain, you're continuous in all these different functions. And so the only things that you need to worry about, about non-continuity for, in general, we worry about it for piecewise functions. And a lot of times, you know, for the piecewise functions, you get weird things that happen, they break, and then you start thinking about the limits, and limit from the left side, limit from the right side, and stuff like that. So if you have a function that has a hole in it, it would not be continuous, but the limits could still exist. So we have this idea about limits existing tied in with continuity. So let's take a look at what happens to limits in higher dimensions and where things can go wrong. So I'm not going to talk too much about where it's continuous. I'm more interested to figure out what happens where it is not or might not be continuous. And then let's first take a look at limits. So first of all, the idea of limits is kind of different. There's similarities in things that might be the same. And in calculus, we studied limits, and I don't know if you guys studied epsilon deltas in detail, but if you're a math major, then you should think about reading over that once in a while before you go and transfer and get into those higher upper division math classes. If you're not, I guess you don't have to worry about it. But in general, when we do limits, all we do is plug in the values, right? And if we plug in the values and everything's kosher or safe, then everything's kosher. Kosher. What's kosher mean? No?
It's prepared in accordance with
Yeah. It's a holiday today, isn't it? It's a Jewish holiday or something like that?
I'm Jewish.
What's it called? Yeah, is that today? I don't know. All I heard was the Supreme Court justices are not working. This is supposed to be their first day of work, but they're not working because of the Jewish holiday. All 8 of them. Anyways, if it's easy enough to just plop in the numbers and you don't have anything to worry about, then you're all good, right? But then once you have an issue, where you put in your numbers and you get something that's indeterminate. And unfortunately, this isn't as easy as L'Hopital's rule. We just take the derivative of the top and the bottom because, first of all, we don't know derivatives yet, and second of all, it doesn't work for functions of more than one variable. So we have an issue here. And so what we want to do is we want to take a look at now, let's get deeper into the idea of a limit as x approaches something. Now let's go back to this example. Since it's a z is equal to x squared plus y squared is a what? It's a paraboloid. And we know that at 0, 0 that your output is equal to 0. So that means limit as x and y approach 0. That means if I have some random x and y point, I can approach 0. Well, I can approach 0 via a straight line. But I could also approach 0 from many, many different directions. You know what I'm talking about?
You go down a skew line.
Your approach has to be flat on the xy plane. We have a slight restriction there because it's the domain. You're on the xy plane. You're in the domain, and if you're at this point over here, these are the drawings that I had. You can approach 0, 0 from many different paths, in many different directions. And unlike back in the good old days, where if you want to approach A, as x approaches A, you can go from one side or the other side. You only have two ways to get to A, right? This is A. You got one way to get to A, another way to get to A. Oh, look, they're both here at the same limit, so the limit does exist there. It's not continuous, but it does exist in this example. Over here, you go from one side and you go to the other side, and now you have two different limits, and so we say the limit does not exist. Right? So remember that? We had two ways, from the positive side, from the negative side, and then we figure it out, and then I say, okay, it exists or it doesn't exist. Now, in 3 dimensions, your domain doesn't just come from left to right. If I want to get to 0, there's many ways to get to 0. Okay, so that's a little bit tricky. So let me count the ways. Is that a poem or something? Oh, how I love thee. How I get to 0, let me count the ways. Actually, there's an infinite number of ways to get to 0. Let's take a look at a couple of them. What if we approach 0 from the x-axis? So if I am defining a path on the x-axis, what can I say about my xy? If you're on the x-axis, y is equal to 0, right? So let me take a look at a path where y is equal to 0. Let's see what happens there. So we'll take the limit as xy goes to 0, 0, and I'm going to change some things here. X squared minus y squared over x squared plus y squared. Now, I said my path was y is equal to 0. So why don't I change this y into 0? And therefore, since y is already equal to 0, I have the limit as x approaches 0, because the y is already 0. I don't need to worry about that, of x squared minus 0 squared divided by x squared plus 0 squared. So if y is equal to 0, let me just replace all the y's to be equal to 0. So now I have a regular limit that I know how to deal with, right? X squared over x squared? Seems like 1 to me. So limit as x approaches 0 of 1 is 1. So if I'm writing this surface along the x is equal to, or y is equal to 0 along the x-axis, I'm going to be at a height of 1. Okay? Let's take a different path. This time let's take the path where, on the y-axis, where what is equal to what? Let's take the path x is equal to 0 and see what happens there. We would have the limit as xy approaches 0, 0 of your function when x is equal to 0. Let's change everything to 0, and so under the limit I have 0y, so that's just y. So really I have y approaches 0. And x is equal to 0 squared. What do I get? I get -1 this time. So this is weird. I come along from one path. I'm going to be at a height. Imagine that you and your friend are on this mountain. You tell your friend, I'm going to meet you at 0, 0. And then your friend is on the x-axis walking along this mountain. And then your friend's going to be at a height of 1. And you are walking along the y-axis. And then as you get to 0, 0, you're going to be a height of -1. You're not going to meet your friend, right? So when something weird like that happens, then the limit doesn't exist. So this is equivalent to coming from one side and the other side back in Calc 1, where you have two different limits. This is the same thing, except you're looking at a two-dimensional path. You come from one angle, somebody else comes from another angle, and you don't meet. So the limit cannot exist for that particular example. In fact, it's interesting to look at these graphs, and it's interesting for a computer to try to plot these graphs, because weird things kind of happen. So let's take a look at this graph. Z is equal to x squared minus y squared divided by x squared plus y squared minus plus. So if you see, there's a little kink in the graph. Kink. Let's try to zoom in. See how you're coming from the ridge, or you're coming from the valley and your friend's coming from the ridge, and you're not going to meet because you're going to be at different heights. So some really weird things happening here. We just say that the limit doesn't exist.
Oh, I see.
And really there's no gap. You see that gap there? That's a gap because of the way that this is trying to draw this graph. Really there's no gap there. It's continuous, not continuous. It's together over there. So if you just have a piece of flat rubber and then you stretch it, it becomes continuous. When you start to do weird things like melt the rubber and then things start fusing in a weird way, then you would have something like this where it now becomes non-continuous.
I think that's geometrically possible in this way, isn't it?
It's what?
Geometrically possible in this way.
Well, I mean, yeah, mathematically you can see things like this happening, but from a geometry point of view, it looks kind of weird.
Wait, does that require infinitely thin surfaces?
Yeah, I mean, the surfaces are infinitely thin, but, you know. Oh, everybody's leaving already? Okay. The test isn't going to be graded until Wednesday or Thursday, just in case you're all waiting. I'll talk about the idea of a makeup, because I do allow makeups and stuff next time. All right, see you guys.